So I'm going to talk about science communication a little bit, because that's sort of what I was asked here to talk about. But I usually just talk about space. So I'm mostly going to talk about space, and I'm going to talk a little bit about science communication and about sort of how talking about space can reach people, and that connects to how talking about science in general can reach people, because we as humans are just a curious species. And I'll talk a little bit about the kinds of things that I've found to be very affecting of people and why that's important. So I'm going to start with a little story. A couple of years ago, I was asked to appear on a podcast for children called Tumble, and this podcast, it's a science podcast where children ask questions and then they bring scientists in and have them explain the answers to these questions in ways that children will be interested in and understand. And I was asked about the edge of the universe. Like, what is the edge of the universe, or how do we find it, or what's beyond that? And so I was doing this interview for the podcast via Skype, and so I had this like Skype video thing with the person, and I was explaining how we don't think there really is an edge to the universe, at least nothing that we've seen, and the universe might go on forever in space, but there is kind of an edge to our understanding of the universe, and as I was going through this, I started talking about the sort of distant future universe and what's going to happen in the future, and I got into a sort of discussion about dark energy, and there are galaxies in the universe. We live in a galaxy. This is a picture from the Hubble Space Telescope of tens of thousands of galaxies. There are a couple of stars in this picture too. If you're an expert, you might be able to spot them. That's one. Pretty much everything else in this picture is a galaxy. That's a galaxy, that's a galaxy, that's a galaxy, that's a cute one. That's a galaxy, I like that one. So our universe is huge, it's full of galaxies, full of stars. And when we look at images of distant galaxies, we notice something interesting, which is that the universe is expanding. And we can sort of map out how the universe is expanding. And the way it's expanding is that galaxies are getting farther from each other. This is my very high-tech animation of that. They're not getting bigger themselves, but the distances between galaxies are getting farther apart. And the way that's happening is really weird. It has to do with something we call dark energy. Basically, the space between galaxies is getting bigger and bigger all the time, and based on our previous understanding of the universe, it should be that the expansion should be slowing down, because the expansion was kind of set off by the Big Bang, and over time, the gravity between galaxies should kind of try and pull things back together. So the expansion should be slowing down, and for several billion years it was, but somewhere around 5 billion years ago, it started speeding up. And we don't know why that happened, but we call it dark energy. Whatever's making the expansion speed up, we call that dark energy. And based on our understanding of dark energy, in the very distant future, the galaxies are going to get so far apart from each other that every galaxy is going to become more and more isolated. Our galaxy is going to become more isolated from other galaxies. This doesn't count the Andromeda galaxy, because the Andromeda galaxy is actually coming toward us, and it's going to collide with us in about 4 billion years, and that's going to be really exciting. But beyond that, other than that, all the other galaxies are moving away. And after the Andromeda collision happens, our galaxy will get mixed up in that, and a couple of other little galaxies nearby. But then over time, we're going to be more and more alone. And all the galaxies are going to be more and more alone. And if dark energy keeps going the way it seems to be going, then the universe will get more and more empty and more cold, and each galaxy will be isolated, and it won't be able to form new stars because there won't be any new gas coming in to form new stars, and so the stars that are in each galaxy will kind of start to fade away and die, and then particles will disintegrate, and the universe will be this very cold, very empty, very dark, lonely place. So I was explaining this to the presenter for this podcast, and I was getting really caught up in the science of it, the excitement, and I looked at the image on the screen, and she had this look on her face, like, and she said very quietly, she said, I don't think this is suitable for children. and I felt really bad. and I was like, oh, I didn't even think about that. I'm so sorry. And and it didn't help that this is really long time from now, and you try to explain, like, by the time this happens, like the sun will already have swelled to red giant phase and engulfed Mercury and maybe Venus, and it'll boil off the oceans of the Earth, and the Earth will be a lifeless husk, and that doesn't help. That doesn't make it better. It doesn't, or you and everybody and probably all humans will be dead. Doesn't help. And it's funny because as a physicist, my work is equations and mathematical models and stuff like that, and so it doesn't always occur to me that instead of being this kind of dry, boring thing a lot of people think of physics as, it can be something that's so emotionally affecting that is dangerous to talk about in certain company. But the thing is that we care about the universe. We look into the sky and we see the motion of our planet reflected in the apparent motion of the stars and the galaxy. We see other stars, we see distant galaxies, we peer into this vastness, and it affects us. It makes us feel things. We look at other planets and we imagine going there. We send probes to take incredible pictures, and we stare at these things, and we get really personally caught up in it. We look at this and we see a heart on the face of Pluto, and people have feelings about Pluto, very strong feelings about Pluto. And then, we want to reach out and touch these things. We want to be part of that. We have, as human beings, an instinct or a basic fundamental need to explore, to learn about the world around us, to learn about the universe, to learn about where we come from and where we're going. And we take that very personally, even if it's stuff that has no effect on our life in the little span of years that we're on this planet. We care about where we came from. We care about where we're going. We care about the beginning of the universe and the end of the universe, just fundamentally as people. And asking the questions of where we came from and where we're going, and asking the questions of how it all works. How does the universe work? What are the basic rules of existence, and what's fundamentally going on? Asking those questions fundamentally changes us and changes our outlook. This is one of my favorite space images. This is from Apollo 17, which was the last mission to the moon. And it's one of the most distant images of our planet ever taken by a human. When astronauts go into space, they come back and they sometimes talk about something called the overview effect, which is this thing where seeing the Earth from space changes how you feel about humanity, about existence. They say that it gives you a sense of connectedness, feeling of bliss and timelessness. They say that it makes you see how we're all together on this beautiful little oasis in the darkness. And they describe it as kind of an interconnectedness or a euphoria. And that's just from seeing our planet in a different context, from changing our perspective. And as an astrophysicist, I can't send people to space. Can't even send myself to space. I've been trying really hard. NASA has not accepted my application yet. But I can sometimes try and give people that feeling in a little way, just by showing them more about sort of where we are in the universe. I can try to. I love this picture. I don't know if anybody knows it. This is Kyle Hill. He's got a very popular YouTube channel where he talks about science of pop culture and stuff. This was an occasion where we were at a science communication conference, and somebody brought a huge pair of binoculars, and I said, oh, we should go look at Jupiter. And so we went and looked at Jupiter, and we could see the moons around Jupiter. So you can see in binoculars, so you don't even need like a big telescope. You can see the 4 Galilean moons of Jupiter, the biggest moons. And you know, I was explaining how when Galileo observed the moons of Jupiter and saw them on different nights and saw that they were in different positions, this was one of the first observations that really showed we're not the center of the universe, that there's stuff moving around something else. And he showed by showing that the moons are moving around Jupiter that we can't be the center. We can't be the center of all motion in the cosmos. And that changed his perspective on the universe. And we can see that ourselves. We can look into the sky and see that and you know, sort of feel that. So, you know, I can try to show people that. But you know, I can't send people to space. But there is this sense that understanding where we are in the universe and understanding our place in the cosmos and sort of changing that perspective can change how we feel. So there's a talk that I give a lot when I visit schools and stuff. And I gave this talk at my mom's church a while back, which was an interesting occasion because I realized that some of the things I was saying might be kind of heretical. But it starts with the Copernican Principle, which is an idea sort of popularized by Copernicus, which is that we do not occupy a special place in the universe. This is the part that might be heretical. There's nothing special about where we are, and in particular, there's nothing special about any particular place. But for us, you know, we're not the center of our solar system. You know, there's the planets go around the sun. We're somewhere sort of in the middle of the array of planets. Nothing's revolving around us except the moon, a whole bunch of satellites. We live in a galaxy. We're not the center of the galaxy. We're kind of out on the edge. This is just an illustration. We can't take pictures from outside our galaxy, but you know, we're something like 26,000 light years from the center of the galaxy. There are, you know, billions of other galaxies out there. We're just one of many. And we can actually map out where the galaxies are in the universe from surveys of galaxies. This is one of these surveys. This is the data from the Sloan Digital Sky Survey, zooming through the data as though we're zooming away from Earth and seeing all these galaxies flying by. And these galaxies are real galaxies. Each one of these things flying by is a real galaxy that's been mapped by the Sloan Digital Sky Survey. And in this survey, they're not looking at, they can't see the whole sky in the survey, so they look in kind of slices. So that's why there's this sort of slice along the center there, and you'll see these sort of fan-shaped slices in other places, but they're trying to map out the large-scale structure of the universe, sort of how these galaxies are laid out in the cosmos. And when we map this stuff out, and when we correct for, you know, the fact that we have a certain perspective based on where we're at, there is nothing special about where we are in the cosmos, in this larger scheme of things. Galaxies appear to be distributed along a kind of cosmic web, this sort of spongy structure, which you can see in each of these slices. We can simulate this actually and see that structure better. So this is a simulation of the structure of the universe, where in this simulation, each of these little bright points might be a galaxy, so you have sort of a cluster of galaxies in the middle. And in these simulations, we can zoom out in a way that we can't in real life. And we can see that, you know, on the very largest scales, the universe looks kind of the same everywhere. And there's nothing special about this part over here or this part over here. They all look more or less the same. And we can look out into the universe and see these structures, and we can see really distant objects, even beyond some of the galaxies where we can actually see, you know, nice, pretty pictures of galaxies. We can see other objects that are bright, shining things far away. These blue dots in this picture are they're central black holes of galaxies that are so far away that we can't even see the galaxy, but we can see that there's stuff falling into a black hole, and the stuff that's falling in gets really, really bright, and so we can see them very far away. And some of these little blue dots are billions of light years away. So a light year is the distance that light can travel in a year. And we use light years as a measurement. Sometimes we use other related measurements in astronomy, but we use those kinds of measurements partially because it helps us to understand not just how far something is, but how far into the past it is. Because when we look at images of distant galaxies, we're looking into the past, into the distant past of our universe. This is because as light takes time to travel, if you see something far away, you're seeing old light. You're seeing light that's been traveling for a while. Turns out that light travels about 1 foot per nanosecond. So if I'm looking at the front row, I'm looking at maybe 30 nanoseconds ago. So you're in the past. In the back, you're way in the past, 100 nanoseconds maybe. If I look at the sun with proper eye protection, of course, I'm looking at 8 minutes ago. If I'm looking at the nearest star other than the sun, I'm looking at 4 years ago. And if I look at a distant galaxy, I might be looking at billions of years ago. And because the universe is more or less the same everywhere, if I look at billions of years ago, at a galaxy that the light left at billions of years ago, I'm looking at what the whole universe was like billions of years ago. And so I can learn about the past of our universe by looking at distant objects. And you might sort of think, well, okay, the universe isn't infinitely old. We know the universe had a beginning, the Big Bang. It's about 13.8 billion years ago. So what happens if you try and look too far? What happens if you look before the first galaxies? There's a nice diagram of this that NASA put together, where you have the Hubble Space Telescope there, and there are different sort of images of distant galaxies, and they're looking at the age of the universe when it was much younger. So some of the most distant galaxies we can see existed when the universe was only 500 million years old. It's at 13.8 now. But we can look beyond that. What happens if we look all the way to the time of the Big Bang? I mean, the Big Bang theory is the idea that in the very distant past, the universe was hotter and denser than it is now. The universe was smaller, and it's been expanding, and when it was smaller, it was hotter, and all the radiation was concentrated, and the whole universe was kind of this fiery plasma in the beginning. And so if you look far enough away, you can look at a part of the universe that's so far away that the light left it so long ago that from your perspective, it's still on fire. It's still in that hot plasma state. And we can do that. We can look into the universe and we can see in every direction, we can see radiation coming from a time when the universe was still on fire. And we can map out that radiation. And we can put it into this zoom out map. We can see it as this sort of hazy glow around the edges of our observable universe. And we can map out where it's a little bit hotter or a little bit colder, where parts of the universe in the very beginning were a little bit more dense or a little bit less dense. And we can put that into a stretched out map like we do for maps of the Earth. And we can say, okay, this part over here was a little bit more dense, that part was a little bit less dense. Let's take this map and let's sort of zoom in on parts of it and put it into a computer and let gravity happen in this computer simulation. And over time on this computer simulation, we get the cosmic web. So we can look at the Big Bang itself. We can look at the time when the universe was hot and dense and glowing with heat and plasma, and we can map that out, and then we can put all that information to a computer, and we can get the large-scale structure of the cosmos that we actually see in our telescopes today. We can make all those connections. One of the things we find when we do this kind of simulation, when we look at the patterns in the cosmic microwave background, that plasma sort of distant plasma glow, one of the things we find is that none of this works out unless most of the matter in the universe is invisible. And then we have other evidence for that too, but it seems that most of the matter in the universe is something called dark matter. So it's probably some new kind of particle that just doesn't interact with light, but it's got gravity, and it holds galaxies together, and it underlies this whole structure of the cosmic web. And most of the matter in the universe, like 85% of the matter in the universe, is this invisible dark matter. But we have really good evidence that's there from things like how galaxies move around and from simulating the progress of building a structure in the universe. So most of the matter in the universe is this invisible dark matter. And we also know from the expansion of the universe that dark energy is a lot of what the universe is made of, and we don't know what dark energy is at all. We call it dark because we can't see it and we don't know what it is, but it's something that's making the universe expand faster. But we can also use the cosmic microwave background and simulations to map out how much dark energy is out there. And we find something really disconcerting, which is that if you make a pie chart of everything that's in the universe, the vast majority of it is dark energy, and then there's most of the matter is this dark matter that we also don't understand and can't see. And then there's this little 5% slice that encompasses everything we can see and touch and interact with in the cosmos. We are part of this little 5% slice. So when I talk about the Copernican Principle, how we're not in a special place and we're not special in the universe, like, we're really not special. Like, we are so insignificant. We are not even an important part of this little tiny 5% slice of the universe. One of the pictures that I think illustrates this a lot, even though it's only visible matter in this picture, is this one, which you might be familiar with. This is the pale blue dot. So this is a blow up of that there. This is just a couple of pixels in an image taken by the Voyager spacecraft from 4 billion miles away from the Earth. And Voyager was looking back toward the sun to try and catch a picture of the Earth from that distance as it was sort of floating away from the solar system. And it managed to capture this picture of the Earth as just a tiny little dot in space, sort of in this little sunbeam from the sun. We are a speck of dust on a speck of dust. We are vastly unimportant in the grand scheme of things. And this might be a depressing idea. It might be a depressing idea that the universe is going to end, and also we're really unimportant. We don't matter in any way that makes any sense at all. But I find it the opposite. I find this really inspiring because, yes, we are a speck of dust on a speck of dust. We are vastly insignificant, but we can learn about the universe. We can see the Big Bang itself. We can learn about the existence of dark matter and dark energy, these things that are vastly important in the universe, but we can't interact with directly, but we know all about them. We know how much of it there is. We can map out where the dark matter is. We can map out how dark energy has been working over time. We can look at the Big Bang, and we can use our mathematics and our physics and our computer modeling, and we can see how you get from this faint glow of microwaves at the edge of our perception and create the entire universe and all of the galaxies and clusters that we see today. We can do that calculation. We can understand so much more. We can understand about the beginning of the universe. We can speculate about the end of the universe, even though we are these completely unimportant little beings who have just a little span of years on this tiny little planet that has no significance in the cosmos at all. So I find that inspiring, and I think that it's good to talk about how your perspective can change when you learn about the universe, when you learn about science and how things work, and how that doesn't have to be this dry, sort of tedious thing. We can have feelings about science in a big way, and as science communicators, we can share those feelings with other people, and we can have the joy of of seeing wonder in someone else, and we can express that wonder in ourselves and let people share that. And I think that's a lot more important than, getting across facts and figures and numbers. People talk about science literacy as, do people know this thing or do people know that thing? Facts about about space or about physics or about geology or whatever. And I don't think that's the important part of science literacy. I think that what we want as science communicators is for people to understand why we do science and how we do science and how science can make us feel, and how, even though thinking about this stuff is not going to make a car go faster, it's not going to make anybody any money, it still can be something that fulfills a basic need that we have as humans to understand the world around us and to understand the universe. And that's something that everybody can share. You don't have to be a sort of a privileged, educated person to share in the wonder of discovery and understanding, because that's something that everybody feels and everybody needs. And I think it's important to make that available, and to make it available in a way that people have access to. Not just like, well, my article is publicly accessible, therefore I'm sharing my science with the world. Like, we can make an effort to say, not everybody has the same background and education. We can talk about these things and share in ways that lets people actually access these ideas. And I think that's really important as well. Not everybody needs to do that. Not everybody is good at that or wants to do that. But if you have the ability, I think it can be an incredibly powerful and rewarding thing. So, people will often talk about science communication, how, we should connect things to people's daily lives and news you can use and all of this stuff. I think sometimes there is space for just, it's really cool, and it's out there, and it's interesting, and we can look at, waves in the rings of Saturn by a tiny moon and feel inspiration from that too. And so there are ways to share our excitement and our love and our feelings about science in ways that can really connect with other people. So that's kind of all I wanted to talk about. That I think that this sharing our stories and sharing our feelings and sharing our passion as scientists is something that can be deeply important and deeply rewarding. And we should always do it in an age-appropriate way. So thank you for listening.
So we have plenty of time for questions and discussions. I'm going to let Katie field her own questions, but I'll come around with the mic.
If you have questions about the universe or anything in it, I'm a cosmologist, so that's fair game, whatever.
Yes, Kenneth.
Okay. Sorry, the mic scares me a little bit. So this is actually the first I've seen of that model of the universe, and those two models were generated independently. The one from what we've seen, our slices, and the other one from the heat map of our outer rim or outer view.
So they're both generated in basically the same way. I used two different visualizations. They're done by some of the same people at University of Melbourne. They're done slightly differently and they're visualized slightly differently. But both of those models with the cosmic web, they start with a universe that's just dark matter, but with the sort of the density distribution of spots determined by the cosmic microwave background, by the statistics of that. And then they just let gravity happen. And that's how you get the cosmic web. And then so once you get the cosmic web, then you say, okay, all the high density places, that's where the galaxies are, because the galaxies themselves totally unimportant at this scale. It's all dark matter in the cosmic web, and then you put the galaxies in, and then you see what the universe looks like. And if you compare a map based on those simulations with a map based on stuff we see in the sky, you really can't tell a difference unless you're already an astronomer and you know the patterns in the galaxies. You won't be able to tell.
On, and then let's say in a typical week, how much time do you spend preparing that media?
What media am I on? So, so I'm on Twitter, and I also have a Facebook page that I very rarely do anything with. And then every once in a while, I'm on like a podcast or a radio show or something like that. So maybe twice a month, I do something like radio or podcast. It depends on if something exciting has just happened. Like when Stephen Hawking passed away, I was on 3 radio shows and a TV one. So like that kind of thing changes the statistics. But and then so there's those things, and then I also write for Cosmos magazine, and it's every like 3 months I think I write an article for them, and then every once in a while I'll write something for someone else like Scientific American. And how much time I have no idea. I mean, so the podcast and radio and stuff tends to be like nights and weekends, as does the writing for Cosmos. And then there's like public talks and stuff, and those tend to be also nights and weekends. Sometimes, I gave a talk at a middle school over spring break. So it's kind of science day job, science communication nights and weekends job sometimes. But I have no idea how the actual time balances out, because there's overlap in terms of like, sometimes when I'm, like I get to choose what I write about for Cosmos magazine, and I often choose topics that are related to the research project I'm working on, so it's kind of connects my reading for my research projects with something I'm talking about with the public, and sometimes I get ideas for research projects from writing things for the general public. There's a paper I'm working on now that comes out of something like that. So yeah, it's all mixed in together, and it's very hard to disentangle at this point.
I'll follow up on that real quick. Because in fact, you just touched on this at the very end. I think a lot of times active researching scientists tend to think of science communication or outreach as like philanthropy, like something that they do for other people. And it's certainly that. I mean, people benefit from it for sure. But I think they see it as often very separate from their research and in addition to, but you touched on this at the very end. Are there other ways that you would say your work in engaging the public in science has informed and helped your actual research work?
Yeah, I mean, so sometimes it's just about like ideas and sort of getting a better overall view. So because the work I do is in cosmology and sort of on the border between particle physics and astrophysics, and there's just so much going on that I kind of have to know about everything that's happening in cosmology, which means I need to read extremely widely, and sometimes writing stuff or talking to the public helps me get a better sort of broad understanding of what's going on, and I'm better informed. So that's a perk. I mean, there's also like the sort of psychological aspect, which is I don't know how many people are active in academia, but when you're working on like a research project or PhD thesis or something like that, it can get really lonely, and like people are not being like, great job today, you did, it was awesome that you wrote down that equation. Like that doesn't happen. And so doing stuff like science communication can be really nice, because sometimes when you give a talk, people will be like, great talk, and like, people will get excited about stuff, and then you get to feel like you know some things, because you talked about something that the people you're talking to didn't know, and so you're like, oh, I learned some stuff in my studies, and that's a helpful feeling to have that you don't always get like in your academic life. So it's also sometimes like a much needed sort of pep talk kind of thing to do these sorts of events and things.
Great talk, Katie.
Thank you. Thank you.
Okay, next question.
Hi, sorry my voice is awful right now. I'm dealing with a bad cold. So I'm really sorry to drag politics into this. The issue is my field that I studied and I have an undergrad, have a bachelor's in, is environmental sciences. And right now, due to our, for lack of better words, political climate, it's extremely hostile towards anyone in any remote part of my field. And I admit that I kind of ran away and I'm off doing art right now because I couldn't take it. But do you have any suggestions for getting a civil discourse going on in regards to anything related to a controversial type of topic?
I think that's really hard. That it's something that I haven't had to deal with directly all that much because this stuff isn't that controversial. I mean, sometimes there's a controversy in should we spend money on sending probes to Mars when there are people starving on Earth, and that's a discussion that should be had and can be had. But my work is not particularly politically charged for the most part. There are lots of different strategies that people use. One of the things that's talked about a lot is if you want to reach people who might be sort of on the other side of some kind of political issue, then finding shared values and building trust are kind of the most important things. So, with environmental science, some people have had a lot of luck with talking about aspects of purity of the environment and things like you can get into religious discussions about how we're stewards of our world and stuff like that. So people have used ways to connect with shared values in that way. And I think that, for me, I think that one of the things that I've noticed a lot is, so I was actually gonna mention some of this in the talk. There are all these surveys about how people feel about scientists and science, and the surveys tend to say that people trust scientists. Scientists are some of the most trusted people in civic life, more than politicians and sometimes more than doctors. Scientists are somewhere up with doctors in terms of people trust scientists. But people also see scientists as kind of inhuman. And so you see these surveys and people think scientists are trustworthy in the sense of they're gonna get the science part right, but they might steamroll over people's values and needs and feelings at the same time because they're amoral and robot-like and all they care about is advancing their scientific agenda and they don't care about people. This is a kind of stereotype that comes up, and it comes up partly because that's a very common media trope, and partly because there have been a lot of occasions in the past where in the process of advancing science, people have steamrolled over other people's lives and values and so on. And so I think that the more people get to know scientists as humans, and the more that scientists can portray themselves as humans who just want to learn things and are trying to just learn things, that will help a lot, I think. Because a lot of people, I see all the time people accusing climate scientists of just being in it for the money, and there's no money. Right.
Especially in the United States.
Yeah.
Right now, I don't have a job in my field because there is no money.
Right, and I think that the only, because there's so much evidence that there is no money, the only way that people can believe that scientists are in it for the money is to believe that there's some kind of big conspiracy and that scientists are inherently evil. And so I think that finding ways to connect with people in the sense of showing yourself as a human who is not evil and talking about what you care about and what's passionate, what makes you passionate and what's exciting, and I think those kinds of things help a lot. So there are a lot of efforts out there to more accurately portray what scientists are like. Storytelling, science storytelling, things like the Story Collider, and then there's like efforts like things about what scientists look like, and like Tumblr and Instagram and all of these kinds of things that people get involved in to try to humanize science. I think those things help a lot, because it's hard to believe that somebody is part of a global conspiracy and evil if you get to know them as a person.
So the Science Slam itself is one of those efforts as well.
Sorry?
The Science Slam itself is one of those efforts as well,
Sure,
to sort of show the human and side of scientists through storytelling. I will also say that that's part of what I think makes Katie's presence on Twitter so effective also, because not only, you're posting all this really exciting, amazing science, but on the other hand, then like on Sunday, I was like, oh, Katie's watching Jesus Christ Superstar Live too, Yeah,
and yesterday I posted about how my face fell off when I went outside because it was so cold. Yeah.
Scientists have weather too.
Sorry? Oh, awesome. Well, thank you for coming. But yeah, that's a big part of why I'm on Twitter and a big part of why I don't just talk about science. And I know that, I talk about politics on Twitter, and I'm sure that I alienate a lot of people with that, but I think also talking about politics shows that I am a person who cares about things, which is, again, not part of the stereotype of, cold, feelingless scientists. So sometimes, when I try to explain my Twitter presence to colleagues, and I say, well, I talk about space, but I also talk about a cat I met or something, I think that a lot of times they're like, well, why aren't you just talking about physics? Well, because the thing I'm doing is not just here's science facts, it's like here's science facts, and also, I'm a person who does things, and so it can be weird because sometimes it can feel like oversharing, and it can feel like why should anybody care about this? But it's because people care about people. They care about, little moons of Saturn, but they also care about people. So that's an important thing to do.
Fantastic. Yeah.
So since you bring up controversy, I guess there's a different sense that controversy could be used in regard to, I guess, within a field, it can be an area of key debate of what's going to be discussed in the future, of what's currently unknown. And so in your field, I guess, what are are there key milestones that you're looking forward to figuring out in the next few years, or what are physicists in 10 years going to be really focusing on?
One of the big things right now is this picture, trying to figure out what the heck dark matter and dark energy are, because we don't know. I think we're getting closer with dark matter, that we have a lot of evidence and we have a lot of information about dark matter. Dark energy is a much harder problem in terms of figuring out what exactly it is. But so in my field, understanding dark matter is one of the biggest things right now. There are a bunch of controversies also in terms of the very early universe. So what happened before that fireball state? So the fireball extended till about 380,000 years after the Big Bang, or after the moment of the creation, whatever you call it. There was a first moment. For 380,000 years, the universe was like a giant fireball. We talk about, in cosmology, we talk about that whole period as the hot Big Bang, as the Big Bang theory, as that whole period is the Big Bang. But whatever happened at the very first moment, we don't know. And that's a big topic that people are trying to figure out right now. And then the end of the universe is another one. So I'm actually working on a book right now about the end of the universe. It's going to come out in 2020, published by Scribner. It's called The End of Everything. And in that book, I talk about what the current understanding and sort of questions are about what's going to happen in the very distant future. And I go through a few possibilities and what the evidence is for each of them. And because that's an area of active research where we're starting to sort of solidify around a couple of possibilities and what those would look like, and we're getting new evidence all the time for which way that might go. So that's another big topic. But I think kind of filling in this pie chart is a big part of trying to understand the universe. The other thing is also in theoretical physics, figuring out how quantum mechanics and gravity work together is a really key thing, and what the next theory is beyond the standard model of particle physics. Because right now we're stuck on the standard model of particle physics, which only explains that little slice and doesn't explain the other bits at all. And so if we can figure out what comes next after that, then we'll have a hopefully better understanding of the whole picture. Or maybe vice versa. I'm not sure exactly how that's going to go.
So are there technological obstacles to addressing those questions, or?
Sometimes, so in the sense that, like, with dark matter, we're building new and better detectors all the time. For dark energy, we're building new and better telescopes all the time. There's a galaxy survey called LSST that's coming out in a couple of years that's going to help us understand dark energy better. So there's stuff like that where we're just building better and more sensitive instruments. On the particle physics side, there's talk of building another collider after the Large Hadron Collider, something that's bigger, larger. So that will help, presumably. But I think for a lot of these questions, it's not just like, we don't know what the machine looks like that we need to build. It's like, especially in cosmology, we discover things in studies of distant galaxies and things like that that we can't study on Earth with machines. So it's about getting more and better data, and then also developing theory. Like on the theory side, there's a whole lot of work to do too. Some really interesting stuff going on in theoretical physics that I absolutely do not have time to explain. That has to do with like a better understanding of how fundamental space and time really are in the final theory which we're trying to develop. Really interesting stuff. But that's in terms of like, we need to build the mathematical machinery as much as anything else.
And I assume that the end of everything will be an illustrated children's book. Yes.
No. It will be aimed at the general public who is not terribly, terribly frightened by the end of the universe. So, yeah.
Well, truth in advertising. I think if
Yeah.
you buy a book called The End of Everything, you're probably prepared to.
Yeah, you should be ready.
Understand.
Yeah.
Okay, I think we have time for one more question, and I saw a hand up over here.
Thanks so much for coming, and thanks for your awesome Twitter feed. I'm a very pro-science non-scientist, if you will, and I appreciate it as a layperson,
cool.
and people like you who will take time out of your life to share your knowledge. Apart from the awesome people like scientists who are able to do that directly and share their knowledge as a science communicator that way, do you feel like there's a role for non-scientists in science communication and public communication with science? I know there's a lot of maybe ill will towards like writers and journalists who don't maybe quite understand the scientists as much, or the science as much, and maybe misrepresent things or overblow particular findings. I know that's a thing.
Yeah.
What would you say as a scientist yourself in terms of that role for the non-scientists?
So I think that there's a ton that you can do without scientific training. I mean, for one thing, you can do actual science as a citizen scientist. So there are lots and lots of projects out there where you can be actively involved in scientific research without any background or training by taking part in like data analysis or data collection or various things like that. That you'll sign up on a website, they'll tell you what to do, you'll do the thing, and you might discover something really cool. And so there's definitely ways to get involved in the actual science part. In terms of like supporting science or supporting science communication, I mean, stuff like talking, like political activism for more support for science and science education is really important. Support for education in general, and just kind of sharing your knowledge and passion with other people. One of the things that I think drives some of the bad science reporting out there is that like people need clicks, and everything's driven by clicks and advertising and stuff like that. So if you can support like independent journalism that does good science reporting, that's always really helpful. Support organizations that do good science reporting and that do just good reporting in general, honestly. That's super helpful. So there are a couple of some of the places that do some of the best science reporting are actually like charitable foundations because they don't have to get clicks. but so sharing and supporting good science reporting is always really helpful. And then just, I don't know, be nice to scientists. That's always good. I'm not really sure, but yeah, there are lots of ways to get involved.